Imagine that you're holding a metallic ball. Suddenly though, it drops onto a bowl full of a cold liquid. It could be, for instance, some salt water you're trying to freeze. You can see that it's not your lucky day because at the center of the ball lies a beautiful ring, which will shatter if brought to really cold temperatures. Thankfully, you love mathematics, so instead of just picking up the ball, we'll make a journey to calculate which will be the temperature inside of it, involving the heat equation, spherical coordinates, laplacians, Legendre polynomials, and more. Welcome. Before we begin, I'd like to note something. I'm making this video because when we were taught mathematical methods in university, as physics students, I saw a lot of colleagues who didn't ever understand why we did the things we were told to. What I found most helpful was visualizing the meaning of every step we did on my own. So now I'll try to show that. That's why I won't get into proving anything or strict rigorosity. For that, there are plenty of proofs online or in university courses. Okay, so first of all, let's analyze our situation. It seems obvious that the ball's temperature will change when it enters the liquid. But if we go forward in time, it will tend towards a specific steady state. On the outside, it looks like this. Its lower half is fixed at a cold temperature and its upper half at a hotter one. Inside of it, though, the situation won't be as simple. To first tackle our problem, we need to understand how heat is distributed. We'll start with an easy to visualize example. In here, we have a distribution of temperature along the x-axis. The distribution is clearly inhomogeneous, so if we let some time pass, according to the laws of thermodynamics, which we won't get into in this video, we can see how the heat flows from the maxima to the minima. If we fast forward a bit, this is the so-called steady state. It's how the temperature profile will look like after a long time. Remember how I said before that heat flew from maxima of temperature to minima? Well, now there are none of those. This is clear if we take a look at the second derivatives. You may remember when first taught about derivatives that the second derivative sign gave hints about the concavity and convexity of our functions, or if the extreme points were maxima or minima. Well, now, this is how the second derivative looked originally, and this is how it looks at the equilibrium state. It's 0. The fact that, after a long time, we reach an equilibrium in which the second derivative goes to 0 can be generalized making use of a differential operator, the Laplacian. The Laplacian is defined as what you're looking at right now, where the partial derivatives, as you must know, are the result of derivating our function with respect to the specified variable, and leaving the others as constants. Well, in equilibrium, this sum is equal to 0. In our previous example, there was no dependence on y or z, so they cancelled out, leaving what we deduced earlier. That previous result looks promising, but its application towards analyzing a sphere seems too complicated, as we'd have to use signs and roots. Luckily for us, there's a way to simplify it. What if, instead of using the Cartesian coordinate system x, y, z, we used another one? The spherical coordinate system, like the Cartesian, is based on 3 variables: the radius, the polar or zenithal angle, and the azimuthal angle. As you can see, 2 of these coordinates are angles. This introduces some extra steps we must take into account when analyzing their variations. For instance, take a look at the zenithal angle. When we change it, while keeping the other variables as constants, it is clear that it is tracing a circumference, with the same radius that we defined earlier. You may know then that the length covered is equal to the radius times the difference in angle. This happens with all circumferences. With the azimuthal angle though, you can see now that the circumference it follows has this other radius, which depends on the position considered. With a bit of trigonometry, you can see that this little radius is equal to a projection of r. These factors that we multiplied to the changes in these new coordinates are called scaled factors, and with them we can now go back to solve equations. I have to ask of you to not get frightened by what I'm about to show, as there will be a lot of letters. First, this is what a generic Laplacian really looks like. Here, the h's are the scale factors we deduced earlier, and each of the u's is one of their corresponding coordinates. So, simply substituting with the factors that we already have, we can obtain the following expression, which, in our case, is equal to 0. Now, we'll do some changes, so I'll once again ask you to pay attention. To begin with, we'll do a change of variables. Specifically, you can say that t is dependent on 3 functions, each of which depends only on one of our variables. This could or could not work, but in this case it will. Okay, so if we plug this into the equation we had, we obtain this. Whoa, there were a lot of changes. Don't fret. If you look closely, you can see that I simply moved the factors that didn't depend on some variables outside of their derivatives. If you don't quite understand this, remember how we had defined the partial derivatives. The other components are constants, so we can take them out. Now, before we proceed, let's simplify this a bit. As you can see here, the only dependencies with temperature are the radius and the zenithal angle. No matter how much we spin around the vertical axis, the value of temperature doesn't change. This knowledge allows us to remove the dependence on the azimuthal angle, which, added to other simplifications, leaves us with this more comfortable expression. Now, each term depends only on one variable. As such, each term will be independent. Think that theta and r aren't tied to each other, so it would make no sense for them to depend on one another. So each one will be equal to a constant, which I choose arbitrarily to be like this, and you'll see later why. Let's solve them, shall we? We'll start with the second term. In order to find solutions for it, there's some work to be done. I'll leave it as an exercise to you, the viewer, which I recommend doing in order to practice changing variables and derivating, as I assume you know how to do that at this level. Here's some hints though. You can do these changes of variables, and remember the trigonometric property that sinus squared plus cosinus squared are equal to 1. If you do that, the result will be as follows. To solve the equation, we'll make use of Frobenius' method. First, we'll set up a hypothesis that, once again, may or may not work. We'll say that y is of this form. You may have studied this already. If so, you'll identify that this is a Taylor series. If not, I'll explain. We are saying that y can be expressed as an infinite sum of all the positive powers of x. The a's represent the coefficients, which can be completely different from one another. To solve the equation, just remember that the derivative of a sum is the sum of derivatives, so dy dx looks like this, and so on and so forth. You can go on with this process. The goal will be to end up with a sum of these summations, with the same power, so that each term cancels out. It becomes clearer with an example. I know there have been a lot of letters until now, but we're close to the finish line. If you want it, you could do as I showed, and you'd end up with this expression. Now, one last step. This expression generates an infinite amount of coefficients, based on some base values. However, it can be proven that the series they generate does not converge on x equal to 1. So we'll truncate them and say that k squared is equal to n times n plus 1. You may ask, which n? There are infinite of them. And that's true. We'll tackle that problem later. The thing is that, fix this, all the coefficients from n forward will be 0, and we'll end up with a polynomial. These are the so-called Legendre polynomials, expressed this way. We are almost there. We just need to solve the radius equation. I'll just skip over the steps and show you that the solutions are these. You can check the validity of these, of course, substituting in the equation. Now, because our sphere includes the point where r is equal to 0, the second term would give us a division by 0, because the exponent is negative. So we'll just remove it and leave the solution like this. Now, all the results we obtained were dependent on a variable, n. Which value is it? There's no reference to take it from, so in theory, it could be any whole number. Let's go back a bit. Remember that this n was associated with a certain polynomial, so for each value of n, we obtain a different one. May it ring a bell if I mention the name Taylor? Taylor approximations show us that, under certain criteria, most functions can be approximated with an infinite sum of degrees of x, which is to say, polynomials. Then that's it. The last step we need to do is sum all the possible solutions multiplied by some constants. And here's how we'll do it. Please note that for these steps, I'll be assuming the radius of our sphere to be 1. For other values, you just need to normalize the r factor. So, this is our sphere. Remember? What info do we know about it? Well, it's surface temperature, the one you're seeing right now. Mathematically, we can define it as a function of the zenithal angle, like so. For the temperatures, well, we are working with a specific example. Remember? So I'll tell you. The lower one, the salt water you were trying to freeze in the beginning, sits at 270 Kelvin. The upper one, the ambient temperature, is at 290 Kelvin. Actually, to make it easier, let's do a little trick. Now, we only have to care about the hot part, because the function at the other will be 0. The final touch comes from a bit of Sturm-Liouville theory. It's too outside of the scope of this video, but you can look it up, and I'll attach anything I see that's useful in the description. Voila! And that's all. You can input this into any able software, or try it by hand up to a certain index. And finally, there it is. This is what the temperature distribution will look like inside the ball, computed up to 30 terms. Isn't it amazing that we could do that? For me, it was. We were able to determine the temperatures inside our sphere using only math. So, to end it all, let's answer the question. If your ring was in the red area, I'm sorry, it will freeze and shatter. If not, you'll be safe. The power of maths goes on to live for another day.